Alright, we're going to see if we can get all of this into one video. If not, it'll be two shorter videos. We'll see how it's going after we get through the first example. The good news is there's only two examples. The bad news is these take some time and space to do. So here we go. Summary of curve sketching. So all the information that we got in 3.3 was about how the derivatives and second derivatives affect the graph, affect the shape of a graph. We're going to put all that stuff together as well as some other pieces and actually be able to now sketch a curve accurately based upon all the calculus that we know how to do now. So curve sketching. Here's the deal. If we were just to use a table of values for a curve, certain essential features are going to be missed or may be missed, such as your maximum and your minimum values, because a table of values, unless you set it correctly, may not be able to count at the right exact intervals that you needed to count at. And remember, the other thing is you cannot normally show the entire graph. Now this is obviously if you're doing something and trying to work it out by hand, and just creating a table of values by hand. Calculators can obviously help you out, and if you had a calculator, you just plug the function in and see what it looks like anyway. But we're talking about if you had to do this by hand. So if you had to create a table of values by hand and you're just going to do all whole numbers or something like that, it's going to miss certain essential characteristics of the function. And even if you tried to, go by better intervals, it's still going to be tough to do by hand. So we can still do it using calculus. The key pieces of information that we're going to need. Guidelines for sketching a curve. You're going to need to have somewhat of an idea what the domain is. Remember that the domain of a function is the set of all of your x values in general, but it's typically your x values, but it's really all of your independent variable values. So it's the set of all x values. Your x and y intercepts, well, your x-intercept, if you want to find the x-intercept, you're going to set f of x equal to 0 and solve it for x. And remember, if it's a function, you can have several x-intercepts. So you'll set basically y, which is f of x, equal to 0, and solve it to find your x-intercepts. To find your y-intercept, this is the easier one. You're simply going to plug 0 in for x, and then you'll get your y-intercept. Alright, number 3, while it's not essential, is a good thing to know. Your symmetry, we talked about this way back in the beginning of the class. We were doing some of the algebra stuff in the beginning. Remember that even functions are defined to be that f of negative x equals f of positive x. So in other words, it makes no difference which way you go on the x-axis, either a positive x value or a negative x value, you're going to get out the same y value. So even is symmetric to the y-axis. Odd is when f of negative x equals the negative of f of x. So in other words, if I plug in a negative x value, I get out a positive y value. That means that if I plug in a positive x value, I get out the negative y value. So they're exactly opposites. The points, every point would be exactly the opposite ordered pair, which is going to be symmetric to the origin. It means that if you took the entire graph and rotated it 180 degrees, it would look identical to the way it was when it started. Okay, again, not essential, but a good idea if you know those. Vertical asymptotes, horizontal asymptotes, and this thing called a slant asymptote, which I'm not sure whether you've dealt with or not. If not, it's not that difficult to do, but it does come up. A vertical asymptote. So a vertical asymptote is going to occur anytime the denominator is made 0, as long as the numerator is not 0. So we'll say that our denominator, whatever that is, equals 0, but the numerator does not equal 0, because if they both equal 0, it's a whole, not a vertical asymptote. Okay, horizontal asymptotes. Let's do this in a different color, and we'll put the horizontal asymptote up here. A horizontal asymptote, remember that a horizontal asymptote, now that we've done calculus, is really a limit of our function as x approaches either infinity or a limit of our function as x approaches negative infinity. So you really could have two separate horizontal asymptotes. And then a slant asymptote, this one only occurs if one specific thing happens. If you have a function where the degree of your numerator is exactly one bigger, so it's greater than the degree of the denominator by 1. So that means, like, if you started off with x cubed plus 2 over x squared, x cubed is 1 bigger than x squared. So you're only going to get a slant asymptote when the degree of the numerator is exactly 1 bigger than the degree of the denominator. All right, after the stuff we did in the previous section, intervals of increasing and decreasing, we should now know that all that stuff comes from the first derivative. Local max and mins, we can technically get from either one of the derivatives, depending on if you use the first or second derivative test, but local max and mins are going to be either where f prime of x is 0 or where f prime of x is undefined or doesn't exist. Concavity and inflection points, we now know both come from the second derivative. And then after we have all this information, which is quite a lot, we can sketch the curve. All right, so let's go to our first example. We'll kind of refer back to this stuff. I probably won't flip the page back and forth. You guys will have a copy of that in front of you as you do these. At least hopefully you will. We're going to sketch the curve y equals 2x squared over x squared minus 1. All right, so let's start off with some of the basic stuff that we need. We need the domain. We need to know what we're allowed to use and what we're not. Well, looking at that, it is a rational function. The denominator can possibly be made 0, so we have to consider that. So the domain of this thing is going to be all real numbers except what makes the denominator 0. Hopefully you guys can see x squared minus 1, positive and negative 1 are going to make the denominator 0. So this is going to be all real numbers except x cannot be plus or minus 1. Now you would probably never really write it that way. You would write out the interval notation. It takes a little bit longer, so I'm not going to do it in this case. But as long as you understand your domain basically is excluding positive and negative 1, that's what we're going for. All right, we need the y-intercept. Y-intercept is the easier one. You simply plug 0 in for x. Plugging 0 into the numerator and to the denominator would give you 0 over negative 1, which is still 0. So your y-intercept is 0. To find the x-intercept, you need to take your fraction and set it equal to 0. So 2x squared over x squared minus 1 equals 0. In order to have an x-intercept, it's where the numerator is 0 only. Not the denominator, just the numerator. So really, that's where 2x squared equals 0, and that, of course, is just 0. That should really make sense. If I had a y-intercept at 0, the x-intercept is also going to be 0, at least at one point, because it's going to be the origin. We could have had other x-intercepts, but we don't in this case. All right, to find vertical asymptotes. Vertical asymptotes occur when the denominator can be made 0, but not the numerator. Well, we've already kind of looked at that when we talked about the domain. The denominator is going to be made 0 when x is positive and negative 1. So x equals 1 and x equals negative 1 are my vertical asymptotes. Horizontal asymptotes. Okay, this thing is going to have horizontal asymptotes as we take the limit. So it's the limit as x approaches infinity of 2x squared over x squared minus 1. Hopefully you guys know from all the flashcard all the flashcard stuff that we've been doing. You're looking at a limit as x approaches infinity, looking at the highest powers on the top and bottom, which are the same, so you're going to divide the leading coefficients. So your horizontal asymptote here, that limit is 2. Your horizontal asymptote is the equation y equals 2, horizontal line. All right, so now we need to start figuring out the rest of this stuff. We're going to need intervals of increasing and decreasing, local max, local min. We're going to need concavity and inflection points if we have any of that stuff. All right, so let's do some work over here on the right-hand side. This is all the preliminary stuff. That's all the stuff that we can, for the most part, do without calculus. The horizontal asymptote is really calculus. Everything else really isn't. So that's kind of the algebra behind it. All right, in order to do this, y prime, we're going to need that for intervals of increasing, decreasing, and max min. Quotient rule, derivative of the top times the bottom minus derivative of the bottom times the top all over the denominator squared. Okay, and we need to figure out where that's either 0 or undefined. Those are the places that we're going to have critical values. So let's simplify this because right now it's kind of messy. So that's going to be, what is that, 4x cubed minus 4x minus 4x cubed over x squared minus 1 squared. Well, that numerator is going to simplify relatively nicely because the 4x cubes are going to go away, leaving me with negative 4x over x squared minus 1 squared. So remember, we need to figure out where this is either 0 or undefined. So we're checking both the numerator and denominator. And all the previous stuff that we had done in the last section, the denominator didn't have to play into it. It does now. So I'm going to have a critical value when the numerator is 0. That's setting negative 4x equal to 0. And of course, if I set negative 4x equal to 0, x would have to be 0. So I have a critical value at 0. I also have critical values from the denominator because what makes the denominator 0 is still plus and minus 1. Okay, it doesn't matter that I'm squaring it at the end because I'm still going to get 0 in the denominator. So my number line is going to include 3 values: negative 1, 0, and positive 1. All right, we got to test values around it. Again, try and go to the most simplified form that you can. This is still kind of like our factored form. It's the most simplified version of what we've got. If I test values around negative 1, so I'm going to test something to the left, which is negative 2. Again, think about what you've got in your denominator. If I plug anything in that doesn't make the denominator 0, it's going to be positive because I'm squaring it. Okay, it doesn't matter what it is on the inside of the parentheses. Once I get that value, I square it, it's positive. So really, the numerator is the only thing that's going to affect the increasing and decreasing here values. So if I plug in negative 2 into my numerator, I get negative 4 times negative 2. Again, I don't care that it's 8, but it is positive. So that's increasing. Plug something in between negative 1 and 0, like negative 1/2. Once again, the denominator is always positive. If I plug negative into the numerator, I get a positive value. So once again, it is increasing. Really hadn't seen that yet. We have an increasing and an increasing. Then if I plug something in between 0 and 1, like positive 1/2, the numerator is now negative, so it is decreasing. And then something greater than 1, like 2, again, the numerator is negative, so once again, it is decreasing. Okay, that's kind of interesting, the way that's working out. All right, I have enough information. I'm not going to do it yet, but I have enough information to write the increasing and decreasing intervals. I have enough information to write local max and local min places as well. I'm going to wait and do that in a second. I'm going to do it all at one time. So I'm going to go ahead and move to the second derivative now so I can get all the hard stuff out of the way. Second derivative, I'm going to take from this guy right here. I'm not going to try and take it from any of the other pieces. It's way easier. So it's still a quotient rule. Let's see, the derivative of the top, negative 4, times the bottom, x squared minus 1 squared minus the derivative of the bottom is now a chain rule. 2x squared minus 1 times the derivative of the inside, which is 2x, times the top, which is negative 4x, all over the denominator, x squared minus 1 squared squared, which means to the fourth. Definitely want to clean that up. Okay, and we did run into this part that I'm getting ready to do in the last section. What I can see is that I have an x squared minus 1 in all three terms, the top two terms and the bottom term. So I'm going to be able to divide one of those out. I've got x squared minus 1 there. I've got two factors of it over here, so I'm going to get rid of one of those factors, which gets rid of the square. And in the denominator, I have four factors, so I'm going to get rid of one of those, which is going to leave me with a cube. That's going to make it easier to simplify that numerator. So now I can distribute the negative 4 into the first one, so that's going to give us negative 4x squared plus 4. And now I have to multiply the 2, the 2x, the negative 4x, so that's really a negative 2 here. So that's going to be positive 2 times 2 is 4, times 4 is 16. We get positive 16x squared. And then my denominator, x squared minus 1 cubed. Okay, let's keep simplifying that because that's definitely going to work down a little bit more. That's going to give us positive 12x squared plus 4 over x squared minus 1 cubed. Okay, so second derivative, we got to set that equal to 0, or once again find out where it doesn't exist. The denominator still does not exist at positive and negative 1, so those are going to be values that I have to include. The numerator, let's see, 12x squared plus 4 equals 0. Well, 12x squared is positive no matter what you plug in, or the worst 0. Plus 4 is positive. So the numerator in that case is never going to equal 0. So really, x equals plus and minus 1 from the denominator is the only place where I could have, like I said, basically critical values for your second derivative, even though they're not really called critical values. It's potential locations for inflection points. But that's where the concavity could change, so we have to plug those in. So create a number line. Negative 1 and positive 1. So we're going to check, in this case, the second derivative to see what's happening with concavity. So if I plug something in which is less than negative 1, now remember, you're going to go with the most simplified version of the concavity, which is this one. If I plug negative 2 in there, remember that the numerator this time is always positive, right? Negative 2 squared times 12 plus 4, it's always positive. So the numerator really doesn't decide anything. Let's put it into the denominator. So we're going to do negative 2 squared, which is 4, minus 1 is positive, and then if I cube a positive number, it's still positive. So this is concave up. Okay, let's plug in 0, something in between negative 1 and 1. Numerator is positive. If I plug 0 into the denominator, we get 0 minus 1, which is negative 1, and then cubing it is still negative, so I get a positive over negative, which is now negative, which means concave down. And then plugging in positive 2, numerator is positive, positive 2 in the denominator is going to give us 3 cubed, which is still positive. So concave up. Alright, so we can tell from this second derivative line graph that the concavity is changing at negative 1 and 1. However, here's what you have to remember, and this is why we did this in the first place. Negative 1 and 1 are not in the domain of the original function. Therefore, negative 1 and 1 cannot create inflection points. We're not going to get inflection points there. Concavity is changing, but it's actually changing around vertical asymptotes in this case. So there's no inflection points, because there are no points on the graph at negative 1 and positive 1. It doesn't exist. Those are vertical asymptotes. All right, what this has done is given me enough information to actually go ahead and sketch the graph. So I'm going to have to kind of refer back and forth here, going up and down. Hopefully you've given yourself enough room. If not, I apologize. You're going to have to use some other paper maybe here. Let's see what we've got. So I'm going to go ahead and sketch a graph. All right, all the way back up to the top. I know I have a Y-intercept and an X intercept at 0, which means 0, 0 is going to be a point on my graph. So I'm going to go ahead and plot that point first. 0, 0. I know that we have vertical asymptotes at x equals 1 and negative 1, and a horizontal asymptote at y equals 2. So my vertical asymptotes, here's 1, here's negative 1. So I'm going to create my vertical asymptotes there. Close enough for the sketch. And then I have a horizontal asymptote at y equals 2. 1, 2. So I've got a horizontal asymptote at y equals 2. So it's going to look something like that. That's the location of my asymptotes. All right, so now what I can do is I can go to all the other information that I've gathered from increasing, decreasing, all that kind of stuff, and figure out what's going on. All right, so I know that my function, according to this, I got to figure out where I'm at. Okay, I know that my function, according to this graph, is increasing and decreasing based upon this stuff right here. So over here, let's write that out. Increasing and decreasing. According to this, this is increasing on the interval from negative infinity to negative 1. And then it's increasing from negative 1 to 0. So why can I not say negative infinity to 0? Because what happens at negative 1? Graph doesn't exist. You can't go through a vertical asymptote on an interval of increasing if it doesn't exist. So we have to stop and then start again. And then it says decreasing on 0 to 1. And then again from 1 to infinity. What you should notice is there's also only one change of direction, and that happens at 0. So I have no, according to this, local mins, but I do have a local max. Local max at f of 0, which we should already know because it's the location of our X intercept, is 0. If not, plug it back into your original function. You get 0 over negative 1, which is 0. And I'll just list it just to make sure we state it. Local min, there is none, or it doesn't exist. All right, now we need to talk about concavity. That came from the second derivative. We'll need to know where the function is concave up, concave down, and we've already stated that there are no inflection points. So concave up is going to occur, get all that from here. Concave up is going to occur from negative infinity to negative 1, and then again from 1 to positive infinity. And concave down is going to occur from negative 1 to 1. So everything in green over here is going to help us to finish this graph. All right, according to this, the function is increasing from negative infinity to negative 1, and it's also concave up from negative infinity to negative 1. Okay? Increasing from negative infinity, someplace way off here, to negative 1, which is right here. But it's got to be increasing and it's got to be concave up. So it's got to be opening up and going up. Well, we've got two sections that we could be in. We could either be in this section up here, or we could be in this section down here. I can't pick the lower section, and the reason for that is if I have a function which is concave up and increasing, it has to look something like this. It can't possibly do that. Not that it can't go through this horizontal asymptote, because a function actually can go through a horizontal asymptote towards the center. It's only what happens as it goes way out towards infinity that it actually becomes an asymptote. But the problem is, I'd have to have another x-intercept right there, and I don't. So, because of that, one more, the function must lie up in this section. Now the function is increasing and concave up from negative infinity all the way up to -1. And it's going to approach the vertical asymptote as we get closer and closer from the left-hand side. And as you go towards the left, towards negative infinity, it does approach your horizontal asymptote of 2. No other way it could be based upon the information that I just stated. Again, increasing and concave up on that interval. Okay, so let's look at what happens next. According to this, the function is then decreasing. No, I'm sorry, it's still increasing. That's right, this was the weird one. It's still increasing from -1 to 0, so it's still going up after it gets past the asymptote, but now it is, according to this, it is concave down. In order for a function to be increasing and concave down, it must look like that. That's increasing and concave down. So that's what my function has to look like up until I get, according to this, to 0. Increasing from -1 to 0 and concave down. And this is also where it's going to hit its local max at 0, 0. So it is increasing and concave down until it hits 0, 0, which is its x and y intercept. Then it's still concave down until I get up to 1, but now the function is decreasing from 0 to 1. So from 0 to 1, move it down a little more, the function is decreasing and concave down. Okay, and it has to go through that intercept because that intercept not only is the x and y intercept, it is also the local max. So that part of the graph makes sense. And then the last piece of this is what happens after 1. After 1, the function is decreasing, so always coming down, but it is concave up. Decreasing but concave up looks like that. So we're going to go over here, and once again, just like the one that we did before, decreasing and concave up, it has to look like this. It must be up in this top section. It cannot be below this section. It can't cross through the x-axis anywhere down here because I'd have to have another x-intercept, and we don't. So that tells us the section that we have to be in. Of course, the other way that you could figure these things out as far as where these pieces go is you could always just take some points. You could take points left of -1, like -2, and plug it in, and you'd see you'd get a value like right there. Then you could plug in +2, and you'd see you'd get a value right there. But you'd actually have to plug the value in and get the y value out to see where it's going. That would also tell you the general shape and where the graph is supposed to go. But this is a relatively accurate graph based upon the calculus. That is what the function that we started with, what was that, 2x squared over x squared minus 1 looks like. Something like that. Alright, this initial video was about 30 minutes long, so we're going to go ahead and stop this video, and we're going to come back with a second video, but it's just going to be the second example. Again, it takes a little bit of time, but I don't have to do all the initial explaining, so we're just going to do that example. It should be much shorter. Alright.